So let's take a look at these two rational functions here. So it says given the functions y is equal to 7 over x minus 3 plus 1, let's actually just call this guy. Let's define them. I'm going to call this one f at x here. And then the second one is y is equal to x plus 4 over x minus 3. I'm going to call this guy g of x. Just define them in function notation. Just makes it a little bit easier moving forward. So the first step is saying algebraically determine the x and y intercepts of both functions. So I've kind of set this up already here on the left. I'm just going to start with the function f at x and the x-intercept. So the f at x is the first one. We know that the x-intercept, the y value, is going to be equal to 0. So we're going to take that function and we're going to go 7 over x minus 3 plus 1. And then we're just going to work our way until we can get something that says, x equals. We'll subtract the 1 from one side here. We can actually rewrite this. We can say that's x minus 3 is equal to 7 over negative 1. And then we can say x minus 3 is equal to negative 7. Then I'm going to add 3 to both sides. And so I have an x-intercept of, what's that? Negative 7 plus 3 is negative 4. So we're going to have it at negative 4 comma 0. That's my x-intercept for this first function. Okay, so let's determine the y-intercept now. So that's going to be when x is equal to 0. So let's take that function here. We're going to call it function at x. We'll go and evaluate it when x is equal to 0. So that's going to be 7 over 0 minus 3 plus 1. So that's going to be negative 7 over 3. Plus, I'm going to change that 1 to a denomination of 3, just like so. So negative 7 plus 3 is negative 4. So my function at 0 is going to be negative 4 thirds, which gives us a value of a y-intercept just like that. So when x is equal to 0, y is equal to negative 4 thirds. Okay, so we have our x and y-intercept of f at x. Let's do the same for g at x. So for x-intercept on g of x, again, we're going to evaluate it when y is equal to 0. Okay, so the first step is what we can do. We basically, we can multiply both sides here by x minus 3. What that does is that will divide out the common term x minus 3 there, and then this will actually on the left will just produce 0 because x minus 3 times 0 is 0. So we have 0 on the left and then x plus 4 on the right. Now I will just say this, generally when we have an equation like maybe in this form or factored form, whatever is in the numerator, whatever factors are in the numerator will always be your x-intercepts. In this case, all we're left with is x plus 4. That'll tell us where the location of our x-intercepts are. We don't have to worry about the denominator. So in this case, our x-intercept is going to be at negative 4. Or at negative 4 comma 0. And then finally we'll do the y-intercept here, and that's going to be when x is equal to 0. So when x is equal to 0, remember we called this g of x. We're going to evaluate g when x is equal to 0. So that's going to be 0 plus 4 over 0 minus 3. And that's going to be negative 4 thirds. So when x is equal to 0, y is equal to negative 4 thirds. Okay, so the purpose of this exercise was, I want you to take a look here. Take a look at our g of x and f at x functions. I'm just going to grab my highlighter. So with f at x, look at the x-intercept at negative 4 comma 0. Look at g of x. Look at the x-intercept. Do you see it's the same? What about the y-intercept? See how the y-intercept is at 0 and negative 4 thirds? Same goes on this function here. So there's something interesting about g of x and f at x here. And we're gonna see here that there's some similarities, even though they're written very differently. You can see like one is a g of x, you see how it's a nice rational expression. But f of x, it has this plus 1 that kind of pulls away from it. So are these actually the same thing? Can we make them look the same? Well, we're going to take a look below. The first thing I want to do here before we kind of start looking at this is stating the horizontal and vertical asymptotes on both functions. So I have the functions here below. I just want to take a look at f of x to start. Well, what we've kind of developed is, in some of the previous questions, is if you take a look at the base function 1 over x, it looks like that. And it has its asymptotes here and here. Okay, so if we are going 1 unit up, that means we're taking our horizontal asymptote and shifting it 1 unit up. So this is actually the location of our horizontal asymptote, and it's at the line y is equal to 1. Now this guy here means we're going 3 units to the right, which actually means we're taking our vertical asymptote and we're shifting it 3 units to the right. So our vertical asymptote is going to be at x equals positive 3. So we have a location of our asymptotes here. Now, just as a general rule of thumb, our vertical asymptotes always exist when we divide by 0, right? And in this particular case, division by 0 happens with that fraction rational statement there. And what makes division by 0 happen? Well, it's when x is equal to 3. So vertical asymptotes always exist when there's division by 0. Okay, so let's take a look at this statement here. Okay, so like I said, when you have a fraction, you have division by 0. That's going to be my vertical asymptote. So that's going to be my vertical asymptote at x equals 3. Now you can see they both share a vertical asymptote. But the problem with this particular form, which we call factored form, well, the problem is, where's my horizontal asymptote? Is there a way to get that? And there is a way to get that. We're going to have to do a little bit of math here, but it does say to look at this graphically. I'm actually just I'm going to skip the graphic approach here, and I want to show you that these two are equivalent. So what we can do here, I'm going to take a look at g of x. Just going to rewrite it. So it looks like this. So how can we get these things to look the same? Well, what I'm going to do is I'm actually going to do some long division. So this statement right here is saying x plus 4 divided by x minus 3. So if I can write that as a long division statement, I would say x plus 4 divided by, oopsies, that's a little bit long, that division symbol. Let's fix that. There we go. X minus 3. And let's just do some polynomial long division. So let's take a look. What do I have to multiply this by to get me to that? And it's just 1. They're already the same. And then I can distribute that 1. So 1 times x is just x. And then 1 times negative 3 is negative 3. And then I'm going to subtract. X minus x is 0. And then 4 minus negative 3 is 7. We can just say positive 7. So that's my remainder. Okay, so why is this useful? Well, I'm going to show you. Let's just start from the beginning. What we said was, we said x plus 4, basically with this long division statement, we said that's going to be equal to, well, that's our divisor, times our quotient, which ended up being 1 in this case. So x minus 3 times 1 plus our remainder of 7. So from there, what I'm going to do is I'm going to divide everything by x minus 3. So what you have here is these x minus 3's divide down. And actually, if you take a look on the left-hand side of the equal sign here, this is our function g of x. That was our original function g of x. If you take a look, that matches up. So basically what we have then is this statement equals 1 plus 7 over x minus 3. If you take a look, I'm just going to rewrite this in a slightly different order. I'm going to rewrite it as 7 over x minus 3 plus 1. Now, is that the same as f at x? Let's take a look. 7 over x minus 3 plus 1. That checks out. So what we did essentially was we took our factored form rational statement and we did polynomial long division, and we actually rewrote it and manipulated it to look like this. So now we can actually take a look at this and say, oh yeah, there's a horizontal asymptote at 1 and a vertical asymptote at 3. So I algebraically determined that these two sides are equivalent. Thanks.